Okay, so this is ECE2700. I'm Professor Gardner. So I've been a professor for a relatively short time. I finished with my PhD about a year ago from now. My specialties lie in analog circuits, but I also do a lot with digital circuits, what we call mixed signal. So this is a digital circuits class. How many of you don't have to answer if you're afraid of it, but how many of you have taken another EE course before? So most of you have taken at least some EE course. So you won't be too lost in this. We're going to start out today first by going over the syllabus and then kind of moving into some terminology that we'll need to use that if you haven't taken 1270, you might not be familiar with, so some of the basics, and we'll go over that. And then we'll kind of jump into the meat because, right, this is a 3-hour course, so it's essentially 2 lectures crammed into one. Hopefully I won't fry your brains on the first time. None of it's too hard, it's just a lot of information. So I have spent 5 years roughly working in industry. So I'm not just academic. I've worked for L3, which, if you don't know, is one of the larger employers of engineers in the area. I've also worked for small startup companies, a neurotech company that designs implantable neural medical devices. I've worked for a national laboratory doing instrumentation for particle accelerators, various other things. So if you run into like questions about jobs, like getting a job, working in industry, that kind of thing, I'm pretty good at answering them. If you're, say, watching those lectures and you get confused, I am also recording them. They will be posted online. So I have this overhead camera. It worked out pretty well last time. You are not obligated to come to class. I know some people are more or less nervous about COVID. I had COVID almost a year ago now, and it just about killed me. It was awful. So if you're worried about it, I understand. If you have family members you're living with that are old or sick, have cancer, is the case of one of my relatives, and you're worried about coming in despite the protection requirements, you can just watch the videos. They will be made available. Yeah, okay. So I'm just going to start going over some of the highlights, some of the important stuff on the syllabus. I do kind of expect you to read the whole thing. I know it's a lot. It's just part of the world we live in now, I guess. But I'm going to bring up some highlights just so that we're aware. We don't require any prerequisites for this course. You could be taking this as your first electrical engineering course. The grading is going to essentially work on homeworks, labs, projects, midterms, and a final. There is also what I'm calling a professionalism grade, which is essentially, don't be a terrible person. Like, don't insult other people. Don't take your mask off. Just little things like that. I haven't had to use it. It's not really a problem for most students because most people are good people. Just be aware. Be nice to people. Homework. For the most part, you're going to, if you just do the homework, you're going to get at minimum 50%. If you get everything wrong on the homework, you're getting at least 50%. If you do the homework and you get everything wrong, but everything looks mostly correct, you'll get about 75%. Most of the homework grade just comes from doing it and giving it a good try. Only a small portion of it comes from the right answer. I generally, and what I'm going to do is I'm going to just go through and grade, like just spot grade your homework. And then I'll often post the answers. Not always, but if I don't post the answer and you're not sure, reach out to me and I'll post it. I can do it pretty quick generally. Midterms, there's going to be 2 of them. I will be posting a schedule shortly. It's been going through some changes because I've actually changed the book compared to what I've used last time. So this is the book that we'll be using. You'll need the book. This is the book I actually learned digital design from, and I think it's really good. It's a really good book. It doesn't have a lot of superfluous stuff, and I think it's very clear. I do want to warn you that the first, well, what would be 4 lectures, but it's just this week and next week, aren't going to be quite in order as to what the book does. It'll cover the same content of what the book does, but it's going to be a little bit out of order just because this is kind of written for juniors, essentially, that have had a little bit more. So we're going to take it a little bit slower. We're not going to cover the whole book. And if you guys start feeling lost or overwhelmed, let me know, because this is kind of a new course, right, with the new book. And I don't want to make you guys feeling overwhelmed. I really want everybody to succeed and do well. Last semester, I taught the same course, different book. The students did really well. I mean, the average was honestly like a 90% almost without any curve. This may end up being a little bit harder. Again, I don't really know. We'll find out. But this is a fun class. This is kind of a course that really lets you see what you're trying to accomplish with electrical engineering. Electrical engineering can be hard because not everyone really knows what it is, because you tell people, oh, I'm studying electrical engineering, and they go, oh, like an electrician? And you're like, well, no, not really. I mean, if an electrician had to take 4 years of math, then that's maybe correct, but not really quite what it is. The second page, right, is going to give you a topic outline. That'll go more into detail when I put out the schedule. The schedule is going to be a little bit flexible as we move along and see where you guys struggle, because we'll spend a little more time. I tend to build in a couple of buffer days so that if we need to spend a little more time on something, we can pretty easily. Homework. You're going to submit everything online as a PDF. So you're going to need to learn how to make things as a PDF. Easy way to do it really is if you have a phone, you can just take a picture of your homework. Like you can write it out by hand, take a picture of it and submit it. If you have a tablet, you can just write out on the homework, but you're going to need to submit it as a PDF. I have some criteria on the PDF, which is, needs to be submitted as a single upright PDF. I say upright because I don't like them being upside down or sideways, because that increases my grading time a whole bunch. I want your name on it just so I know who it is. I want your answers circled so that they're easy to find. Don't do like columned problems. Do them horizontally separated, like vertically separated. And we're going to be doing code. So I'll talk in just a minute about really what this class is about. But part of it is going to be writing code. When you write code, this number 5 here talks a little bit about how to submit that code, and I'll probably show you some examples when we get closer to needing that. There is a 3-part project that comes at the end of the semester. It's pretty intense, but it's pretty cool, and I'll cover what that is in just a minute. Third page, mostly I'll leave that to you to read. Last page. Bottom of there's this block chunk about lab books. I'm probably going to be changing that a little bit because we're going to be submitting those online as well. The lab, it is possible to do the lab remotely. You don't have to attend. It is much harder, especially the project portion. If you don't want to take this in person and you want to do the lab remotely, make sure you email me so I can kind of talk you through it and explain what we expect. It is a good idea. When I put the schedule, it's going to say what lab we're working on a given week. It is a very good idea to read the lab and at least start on it before we get to that lab, so that you have good questions to ask as I explain it. I have office hours on the first page. Younger students, and I don't mean age-wise, I mean like newer to college, so freshmen tend to not use them very much. So what that means is I'm almost always available during those office hours. I am in my office, but you can also let me know that you want to meet via Zoom online, and I can queue that up and we can meet remotely. If you're struggling or get stuck, make sure to use the office hours, because it's free tutoring is really what it comes down to. Okay, that's all I really want to cover in the syllabus. Let's talk about what this course is. So this course is a digital circuits course. It's an introduction to digital. So you might not even know what a circuit is. If you've taken 1270, you probably have a pretty good idea. Who's taken 1270? Okay, so about half of you. The other ones, doesn't really matter. We'll get into it. You guys might be a little bit more bored for a minute, but you'll be okay. So who knows what an Arduino is? Only like one or two of you. Okay, that's interesting. So an Arduino is what we would call a microprocessor. You might see these in other ways, right? It's basically like the dumb version of a real processor. They're really simple executions, and they can think, right? You write a program and it does it. But the benefit of like an Arduino, it's really a hobbyist tool. So that if you want to, say, control your Christmas lights, you know, if you've seen any of those videos where the Christmas lights are lighting up in cool patterns as the music plays, those are almost always controlled by an Arduino. And they have these digital I/O, meaning in outs. So digital I/Os, essentially the output or input is either a 1 or a 0. That's what digital means, is it's ones and zeros, right? So Arduinos have the ability to be easily programmed. It's easy to access their inputs and outputs usually, and they can interface with the real world. So the end project is actually going to be learning how to make a microprocessor using code. You're going to write what we call VHDL is the language. It's a hardware description language, HDL. Now, is anyone who's here familiar with programming? Okay, most of you. If you're not, this will be a little bit harder of a class, but not impossible. There's actually more of you know code in this one than the last one. So hardware description language, interestingly, is a little bit more difficult if you're a good programmer, because software is not hardware. And what we're programming is hardware. And we'll learn more what that means and the differences as we go along. But be aware that there are going to be some quirks of the language that you're going to catch you by surprise if you're really accustomed to programming in software. But we're going to build up. We're going to build a microprocessor, and it's going to take a series of commands and execute them. It's a really simple version, but you could actually go ahead and throw it on what we call like programmable logic devices, and it would work. So we'll first learn about digital circuits. What does a digital circuit mean? What are they made out of? What does it look like? Next, we'll learn how do you make them, both physically and using code. You can build them with your hands or with code. Either way works really well. And we're going to be using a tool called Vivado. Now, Vivado is made by a company called Xilinx. It's a development suite. So it allows you to write code and simulate it and see what happens. We'll learn a lot about the simulation and testing. Now, the interesting thing is if you take 2700 and 3610, which is another, like the continuation course of this, you're pretty much ready to go out and get a job. Like the industry right now is desperate for people with these types of skills. It's a very valuable course to have. Okay. So let's just go into some terminology. So we have three major concepts when we're dealing with electricity that you just can't get around. We have voltage, V, current, I, and resistance, R. Now, if you've taken 1270, you're bored out of your mind already, and that's okay. So what we can do is pretend that electricity is water. Now, in that analogy, it's easiest to start with I, current. Electrical current is essentially the same as water current. It's the flow of, well, electrons in our case, right? Resistance you can think of as the size of the pipe. So the resistance goes up if the pipe gets smaller. As a result, if you were having, say, a nice big pipe flowing along, and suddenly that pipe shrunk down to a small one, you're going to get a backlog of water, right? Because it can't all flow through. That backlog is the voltage. It's a potential. So they are all related through something we call Ohm's law. That is Ohm's law, where the voltage is equal to the current times the resistance. Now you're going to see this in tons of classes all the time. Now, resistance is a bit weird, and you'll hear me talking about this. Who knows what the unit of resistance is?
It's an ohm.
Ohm. Ohm. Now the other ones are you're more familiar with, right? So current is amps. And what's the unit here for volts? It's volts, right? So those are your units. And you can kind of predict how things are going to behave based on that equation. That tells you a lot of what you need to know about a circuit. Now, we're not going to do too much with this. And if you've done 1270, or when you do 1270, you're going to do a whole lot with Ohm's law. Here, you just need to be aware of it because you can run into issues with current. So you may or may not have heard from, I don't know, television stuff. Volts, you'll hear high voltage danger, right? Volts aren't actually all that dangerous. What is really dangerous is current. But it's not just dangerous to you, it's dangerous to, say, your microcontroller. Because it's going to have a limit on the amount of current it can provide. And if you exceed that current, the device will break. So we need to know how to not break our device by limiting the current. And we can do that by just rewriting the equation. I is V by R, right? So to reduce the current, I raise resistance. You're going to hear me use some terms frequently. The first off is ground. Now, ground can be a couple of things. It could literally like earth ground, but really what it is a reference point. So volts aren't absolute, they're relative. So what that means is anytime if I have a 5-volt battery, let's say I'm holding two 9-volt batteries in my hands. The positive terminal of each of those 9 volts may or may not be the same voltage. What they are is they're 9 volts relative to the negative terminal. So often we'll use that negative terminal as ground, right? That's what I mean when I say ground. Similarly, I'll say power or supply to refer to, or even rail, power, supply, rail, I think those ones, which refer to the voltages that are actually creating the energy for you, right? So the 9-volt battery is providing a 9-volt supply. Have you guys bought your breadboard kits that are part of this? Right, part of the reason you call it the rail is because you have those 2 columns that are vertical rails. We'll go into more into the breadboards as part of next week's lab, so you're kind of familiar with those. But that's where that terminology comes from. Lastly, we have signals. So signals are something that's carrying information. In any electric circuit, you need a ground, you need a supply, and if you want to do anything, it needs a signal. We're going to be talking a lot about digital signals in this class. What's the difference between an analog and a digital signal? Anyone know? What's it? Give me an example of an analog signal.
A sine wave, maybe.
Right, so that's a good, but we could make a digital sine wave. You could.
Yeah,
so,
that's right.
so let's think of a real world example of an analog signal. My voice. I'm transmitting data to you, analog. Now, digital, we know, means ones or zeros. So what is a digital signal? Where's an example of a digital signal? Something you use every day. Yeah.
With a light switch for it.
Actually, that's perfect. That is a digital signal. The light switch is a digital signal because it's on or it's off. It's a 1 on or 0 off. Now, we have another vocabulary term for that. It is either asserted on 1 or deasserted off 0. Now, those terms, for whatever reason, are difficult to grasp. So make sure you get it in your head. Asserted just means on. It just means 1. It just says go. It's like saying, I assert that this is true. And then deasserted is just taking it back. So analog signals, let's go with the sine wave. This, I actually got to go look and make sure that this color is showing up on the monitor. So that, yeah, okay, I guess that's good enough. Okay, so this is an analog signal. I mean, it could be like a wave of water. It could be like my voice traveling through, right? Because it's just making percussion. But the point is that I can pick any value. So if this is 0, and let's say it's electricity. Let's go with this simple one. This is 0 volts. This is 1 volt. And this is minus 1 volt. I could pick, and let's say this is 1 second. I could put any value of voltage and any value of time. Digital signals don't have that luxury. They need something called, well, either a level or a resolution. So what it's really going to look like in digital is it's going to have what we call samples. They are usually, not always, but usually equally spaced in time. Now, I have those samples. It clearly looks like a sine wave, even if I erased all of the continuation line, right? We can recreate signals using these samples. So we can kind of estimate what an analog signal looks like as long as we have enough samples, right? You'll learn later like what the criteria for having enough samples is, but in some ways it's obvious, right? If I only have 1 sample in a period of sine wave, I can't recreate the sine wave. I have no idea. And 2 is pushing it, right? But it turns out you only need 3 and you're good. You don't need to know that. That's just off the wall. Just understand the idea of samples. Now, they're also unable to have every possible value. So what they will do is they will have to pick the nearest appropriate value. So let's say that I have a signal that goes from, we'll just call it a ramp, is what it is. So it ramps from -1 volt to +1 volt. That's what it looks like in analog. In digital, and so on and so forth, because it has these fixed levels. And if I were trying to sample or record a value of a voltage that was here, the circuit would have to decide, does it bump it up to this level or bump it down to that level? Now these levels are represented by binary. So we count in decimal, where we go from 0 to 9 and then use those same numbers over and over again. Binary is 0 or 1 and then just starts counting up. So if we have 0, well, and each number, right? So if I have a 10, we call the 1 in the 10 the tens place, right? Well, we don't have tens place in decimal. What we call them, though, overall is bits. So this is a 2-bit number. I'm actually going to move it a little this way just because of the way I pointed the camera. Okay. Let me see this. Yeah, a little better. Okay, so let's count in binary. Right? This is not 11. This is 0, 1, 2, 3. So we'll do more on the binary representation later. And there are different ways to represent binary. And we'll cover that, I think it's chapter like 5. It's a ways away, but we will get into binary. But you need to be aware of how we count in binary, just because that's what a digital system uses as representation. So when I talk about bits, this is 1 bit, 2 bits. If I wanted a bigger number than 3, I need to add another bit. Now what you'll notice is each column, if I'm trying to count up, which you're going to write a whole bunch in this class, ascending binary. You're going to do this just all the time. So in the zeros place, you're just 0, 1, 0, 1. And as you go each column, you just double the number of sequential repeats. So 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. How many zeros will be in the fourth column if I have a 4-bit number? 8. 8 zeros, 8 ones, if I want to represent all of a 4-bit number. I'm unlikely to ever make you count past, well, it would be 15 to write 4 bits, just because writing out 32 is tedious. Okay, the next, if you have taken calculus, I'm certain you've seen the following representation. Right? Something like this, where you have the function of x is equal to x squared. And we could go ahead and write that. I mean, if you've done algebra, you've probably seen that notation. We're going to be moving towards what we call Boolean algebra. We're not going to be doing any calculus, don't worry. But we are going to be doing something called Boolean algebra. And it's going to use this type of notation. But digital engineers frequently leave off of the f of x portion of it. They just say f equals to something. Oh shoot, sorry, I skipped one thing. So there's an idea in circuits. I mean, it's everywhere, but it's especially important in circuits of serial and parallel. So serial means sequentially, one, then the other, then the other. Parallel means multiple at the same time. Now, when we get to drawing up some circuits, it'll become more like really obvious. But if you picture it like a road in your neighborhood, the road is, in the neighborhood is serial, right? You have one car per lane. The highway, the freeway, is a parallel road, right? Because they'll have like 4 lanes. those 4 lanes are in parallel. Right, that's the general idea of serial and parallel. So all I'm doing right now is getting you caught up on the basic concepts of what you'll need to know, because it's just vocabulary. We'll get into all of this a bit more depth as we kind of progress through, but I like to introduce these ideas so that we kind of come back around and be like, oh yeah, I know what this is. Okay, all right, let me take a drink. Okay, so that pretty much brings an end to the vocabulary section. I'll be using it a lot. You'll hear it, you'll get comfortable with it. But now we're going to start talking about digital logic. Now, logic is this idea of, well, digital logic specifically, right? You have like the philosophy version of logic. They're related to digital logic. But digital logic is just saying that you can describe the outcome based on the inputs, right? The output is predicted by the inputs. Now, if I want to say something like the light was a good example. The digital logic is essentially saying if the light switch is on, then the output is on, right? If the switch is 1, output true. So that as a function is just that, right? Where the output is determined by 1 input. But we have some other ideas, which are and, right? We need to make it useful. So let's say that you wanted to start your car and say it's an automatic, right? The car doesn't want to turn on unless the gas or the brake is pressed and the key is turned, right? Now, the lights in here have the OR operation. If that switch is turned on or that switch is turned on, the lights are on. So, one of the ways this book likes to describe digital logic is by taking 2 statements, 2 inputs, and drawing them into a Venn diagram. Now, a Venn diagram is something simple where you have 2 circles. That was really bad. Sorry, I look like the world's worst drawer syndrome, so work with me on that one. Okay, so let's call this switch 1, switch 2. And we have some function. And we can say, in here, this is switch 1 and switch 2. Out here this is switch 1 and not switch 2. So we can draw those in. This function means switch 1 and switch 2, right? Similarly, if I were to do this section, that's switch 1 and not switch 2. If I say switch 1, well, switch 1 encompasses this whole thing, right? And switch 2 just doesn't matter. And we can start adding more circles to this, and we kind of will as we go along. Okay, so you're going to hear me use these terms, and it's going to be helpful to see them. Where, like, right, I said switch 1 and not switch 2. We want to be able to write that, right? So in digital logic, when we're writing these things, if we want to say something like, well, I'm just going to switch to x's because it's easy. So if I want to say x1 and not x2, and looks like multiplication. So if my function, I want x1 and not x2. Well, this is x1 and x2. If I want not, there's two different major ways that you'll see it represented. The first one is with a bar over it. So that is x1 and not x2. Okay, so this is and. And if you see it in writing, the logical operators are almost always represented with just all caps. So this is and. Similarly, right, I talked about or before. You would say F is x1 or not x2. So or is represented by a plus sign. So let's go ahead and say that I want to if I can do this right. Okay, Venn diagram, 3 variables. What is this region? Take a moment to think about it. What is the logical expression using X, Y, and Z for that region? Take just a moment to think about it. Okay, what is it?
Is it X and Y and Z?
Yes, X and Y and Z. Okay, so now say that I want that region and that region. What do I have to add? Yep, X and Y. How do I connect those two, do you think? I'm going to go for other people.
X, Y, X times Y is 8 times X.
Almost. So that would be a little bit redundant, actually. This is actually a really good point. So if I did that, if they were another ands, X, X. If X is true, can this X ever be false? No, because they're the same variable. They're always the same thing. So we don't want to say this and that because it's repetitive. So we're going to go into some properties shortly, actually, that say essentially that's unnecessary. But that's not how we connect them. Because what this is saying is these two regions are ORed. OR. So I can go ahead and write out the expression for each region and OR them together. What this builds is something that we call a sum of products. Oh shoot, I'm gonna run off the whiteboard, all right. Oh no, I'm good. You'll see it abbreviated SOP, sum of products, right? It's the sum of a bunch of products. If I wanted to add a third region, I would just add another sum, which is another OR. What this Venn diagram is representing is for the function f, when is it true? When is it filled in? When is it assertive? It is true when I'm in the region X and Y and Z, or I'm in the region X and Y. Now, the algebra holds. We can do algebraic operations on the logical operator. So this is equal to right? I just factored it. Now, I've been kind of building up to this. One means true. One, true, asserted, right? Synonyms. What is Z or 1?
It's always going to be 1.
1, yes.
Is that couchism, totism?
I forget the name of it, but yeah.
It's true in every
Yes,
situation.
yeah. It doesn't matter what Z is doing, right? Because it's always 1. And we're going to get out some more tools to make this more obvious to you. But this is kind of building up to some of our logical operator rules. But I'm going to make sure I don't skip anything. Yes. Okay. So this is a little bit of a sneak peek. We'll hopefully get there tonight. I'm going to pull it back from some of the math stuff for a moment. And what we're going to talk about now is, well, we're building up a shared language here, right? We need a way to talk about these things. So we're going to kind of talk about the components of a circuit. So if you were to pull out a computer or open up your phone, right, you're going to have a little probably green board that has little black chips on it. Those are pre-packaged components. They do something, and it might be really complicated. It might be a processor, or it might be really simple, and it might be something that we call an AND gate. Or in other words, it's an electrical device that takes 2 electrical inputs, and the output that's a weird way of explaining it. So I'm skipping a little bit here because I realized explain this. This is how we draw an AND gate. So if I call this A, this B, and this C, then we can write C is equal to, how do I write this?
B times A.
Yes. A and B. Meaning that C is 1 if A and B are both 1. Similarly, we can make an OR gate. Where F is equal to D or E. Meaning F is 1 or true if D or E is 1. Now this is more or less the foundation of how you are able to call somebody on the other side of the world with your cell phone, because it's all digital. I mean, there's some electromagnetic stuff in between, but we can build up really complicated thinking using these gates, and we'll get there. You'll learn how. Yes. So we can take this a step further and start drawing digital circuits. So if we go back and say we want a statement that was X, Y, Z, or X, Y. I want to make a circuit out of that. Well, let's go to the gates. Well, the first one is, let me back up and think about how I want to explain this the easiest way. What you want to look for is how are they connected? The other question is, what is the final gate going to be? Because this is going to be kind of a cascade of gate. If you see this SOP, sum of products, form, the output gate is always going to be an OR gate. Much like the Venn diagram that I built up, you're going to use the components and OR them together. So X, Y, Z, I can draw an AND gate, but this one has 3 inputs. X, Y, Z. I have another AND gate. And I can do this one of 2 ways. I can either just write X and Y again, or I can connect them. Little hoop like that means it's jumping over, right? They're not connected. If you wanted to make it explicitly clear that they were connected, you would write a bubble like that. But we don't want them connected, so let's jump. Okay. That's our circuit, turns out. I've just used my AND gates and my OR gates. And here, this output, right, this is what we would call a component. Each of the AND gates and OR gates are all components. And they output to a wire, or a trace, you might hear it called as well. And this trace or wire, or net is another word that you might hear it used, is X and Y and Z. This net is true if that is true. Similarly, this is X and Y. And the output is this or that, right? So this is how we kind of start building up circuits. And we can start seeing how we can use these circuits to do thinking for us based on lots of inputs. There are a few more components we want to talk about. I really appreciate the calling out the lights example because it's perfect. An important component of any digital system is going to be what we call a switch. So a switch is usually drawn, well, let me just tack it on here actually. Like that. Little lever, right? And you might see an arrow like so. And what this is saying is there's going to be some input that determines if this is a switch is open or closed. Open means it's not connected. It is an open circuit, it's not connected, no current flows through. Closed means it closed and current or voltage can flow through. Nice and easy. So that's our representation of a switch. So now we've got an AND gate, an OR gate, and a switch. But we remember that if I'm building a digital circuit, it has to limit the amount of current. And I have Ohm's law, right? Which I shouldn't have erased. And let's say I want this to turn on a light if this is true. Sorry, if this is true. Let me dump the switch for now. Okay. The way we draw an LED or a light, right, just like your Christmas lights are LEDs or the flashes on your phones are now LEDs, is like so. Now, if you recall, ground is the reference, right? We need to reference it to ground. We do that with this symbol. There are actually other symbols for ground that you'll see. This is the most common one. You can just use a down arrow They all each mean specific things, but I'm not going to get into them. I'll almost always use this symbol, unless I get really lazy. Now, LEDs don't really have any, well, they do, but it's complicated, resistance. Just, you can assume that they have zero resistance, more or less. So if that's true, how much current is flowing through my LED? How much current? If the resistance is zero.
Looking at it, it's a very large number, pretty much an infinite.
Yeah, essentially infinity, right? Because you divide by zero, R, resistance. So we need a new idea so that we don't break the circuit, because no circuit can provide an infinite amount of current. A resistor looks like that, just ziggy lines. Again, represented in ohms. And we can say something like, there's a specification for your LED that has 20 milliamps in it. So let's say my LED breaks if I put more than 20 milliamps through it. Then the question could be, and it's going to get more complicated than this, but let's assume that it has zero resistance for now. Let's say that this is a 5-volt digital output, right? So what that means is on or 1 or true is equal to 5 volts. What value of resistor would I need to make sure that my current is less than 20 milliamps? What do? What's the first step? I have this equation, right? So I can just start putting in numbers. So let's just start with this one. My V, 5 volts, is equal to I, 20 milli, and I can use the milliamps, times R, the unknown. I can then solve for R. So this M means milli. 20 milli is that. This is going to be a very common notation you need to be aware of. So 20 milliamps is equal to 0.02 amps. Similarly, let's solve this out. What is 5 volts divided by 0.02? Someone want to throw that in a number? I mean, it's not that hard of it. 0.02, 25? Or, well, 250, I guess. But
250 ohms.
yeah, okay. Now, if my resistor R is 250 ohms, my current will be 20 milliamps. If I want it to be less than that, what do I do to the resistance to make it less current? Increase the resistance. If I increase the resistance, current goes down. You're going to be doing exactly this in a lab next week, I think. If not, it's the week after that, where you're going to have a real digital chip. You're going to hook up a light, and you're going to need to calculate the resistance. Now, it gets a little bit more complicated. Why? Well, I've been pretending that LED doesn't do anything. The LEDs really have a voltage associated with them that they need to turn on. Once they're on, they will do anything they can to maintain that voltage. For a lot of LEDs, it's something like 0.7 volts. You will get that specification. You'll be told what that voltage is. Now we need to calculate what that resistance is. We do this, don't worry, this is like the most complicated circuit math that we're going to have to do essentially, I think, in this class, is we're no longer going from 5 volts all the way down to the reference ground. We're actually going from 5 volts to 0.7 volts. That's because you can label the notation like this, plus, minus. Meaning if I go this direction, I go up plus 0.7 volts. And then here, I'm going to go up some voltage, right? But that voltage is 5 minus 0.7. So if I do 5 minus 0.7 divided by, sorry, I don't want to do this. No, this is fine. Okay. So I solved the resistor here for the desired 20 milliamps. This will mean that I have designed the resistor from 5 volts to 0.7 volts to have 20 milliamps flowing through this resistor. If 20 milliamps is flowing through this resistor, how much current is flowing through the LED?
Is it the 20 milliamps?
Yes, 20 milliamps. Because much like water, if it's flowing through this pipe, it has to flow through that, right? It can't disappear. We can't make current out of nothing, and we can't disappear it into nowhere, right? So that's what serial means in a circuit. This is a serial circuit. If the current flowing in has to equal the current flowing out. You can't make current from nothing. You can't disappear it to nowhere. It has to continue on through. So you can just design the current for the resistor to protect your LED or to protect your circuit, whatever has the lower current limit. 20 milliamps, I use that as an example because that's a very common number that you will use if you want to be safe on your LEDs. If you had too much current flowing through your LED, what would be a sign that you had too much current flowing through the LED? Take a guess. What might you see?
So you might see it change color from what? I mean,
Not quite. It would change brightness. The amount of current flowing through your LED will change its brightness. So if you hook up a circuit and you have someone else in the lab next to you has like this dim LED and you look down and yours is blinding you, your resistor is probably too small because that means too much current. Cool. Now, we could take this further. We could add a switch here that would break it if we didn't have it turned on. But why would we do that? Because we could just use one of these guys as our switches, right? So we could have 3 switches of X, Y, and Z. And as long as they were X and Y, or X, Y, and Z were all turned on, we'd be good to go. But let's take a moment. Actually, let me see if I'm there yet. Ah, we are. We're getting there. Does that term matter? No, it doesn't. Someone else. Why doesn't this term matter? think about it for a moment. This term is unimportant to f. Think about why. Think back to the simplification that I did the factoring. Yeah.
Because we don't even care about Z because of the second.
Exactly. Because this or means if this is true or that is true, then it's 1. It's true, right? But this, x, y, and z can never be true unless this is true. That makes sense to everyone. So you're going to have to think about this logically a lot, and we're going to start building up some tools to help you do that. But that's the kind of analysis that we're going to want to do. Okay. So I'll leave Ohm's law up there. I'll leave the gates up there. Okay. So we've learned about what these gates do. We've learned how to count in binary. I mean, kind of, right? We covered it. It's not that hard. There's this tool that we use, both for gates and more complicated circuits, that we call truth tables. That kind of comes right from the idea of something is true, 1, or false, 0. The truth table for an AND gate. We draw like so, A, B, C. Now, A and B have a finite number of combinations that they can be. Because it's 2 inputs, that means there's 2 bits. That means we just count from 0 to 3. 0, 0, 0, 1, 1, 0, 1, 1. Now, this is an AND gate. What is C when A and B are 0? 0. And, 0, because it's not AND. 0, still not AND. 1, right? Because it's now true and true, therefore output is true. So go ahead, take just a brief moment, and fill out the truth table on your notes for the OR gate. Okay, so what's this? 0. This one? 1. 1. Yes. Did anyone not get that? Great. Okay. So that's what a truth table is. Now we can actually build up a more complicated truth table, and we will shortly. But because this is taking a gate and going to truth table, we can actually go truth tables and turn them into gates. We'll get there. But let's say I have something more complicated. We're going to take, I believe this, if you guys, I hope you guys all bought the book. This is on the book, page 40, if you ever want to go back and look at it. You don't need to, because I'll just write it. going to have 3 AND gates. An output of an OR gate. And then we're going to have 2 inputs, X and Y. So X, or Y rather, will go here. And then we're going to introduce a new gate. Right? So I talked about the NOT operator, which was the bar. Oh, I didn't actually cover the other one. So X bar is one way. If I'm typing it on a computer, you can make bars on the computer, but it's annoying. X apostrophe, which I say out loud, you say out loud as X tick or X bar. Okay? But we need a gate that does that operation for us. This gate. We call this an inverter. Now this symbol actually derives from this one, which is a buffer. The truth table for this buffer is easy, right? Because I have input A, output B. The truth table, A, B, A can only be 0 or 1. B is 0 or 1. Easy truth table. Inverter is just, well, the opposite of that. Oh, sorry. Just flips it. So if this is X, I'll wait a second while you guys write. Sorry. If I go too fast, yell at me, it's fine. All right, so if this wire or net is X, then this wire is X bar. Doing this is good practice for when you start getting more complex representations of things so that you can keep track of what every wire is. So if this is X bar and this is Y bar, what is this net?
Is it no Y and no X?
What goes, yeah, yes, but what go, we say that not X and not Y. Right, and I can go through and label each one of those. Now, this is the most complicated circuit I've drawn. It's still not that complicated. But as you develop as an engineer, you'll look at that and go, that feels too complicated. Because we only have 2 inputs. How complicated does our circuit really need to be? It feels wrong. But we can go ahead and we can make an equation out of the circuit simply by going through labeling the nets, right? So this is not X, not Y. This one is X, and so X and not Y, and this is X and Y. Therefore, the output F is equal to, take a moment and go ahead and fill that out. What is F?
this is some products or.
Yeah, you'd have a hard time writing it any other way. Possible, but it's difficult. Okay, so what we want to do with this last stage is an OR gate. So that means I'm connected by OR signs, which is pluses, right? And I just have to throw in these terms that we wrote up. So it's just, and the way I do this is I'm just going to go ahead and write XY or XY or XY, and then go back and add the necessary bars to say not. Right? Did everyone get that? Okay. Then we can go and we can actually make a truth table for this. We can make a truth table for F. We haven't done this explicitly yet, but which of these rows are true? Is 0, 0 true? Yes. Why?
No, it's X and Y.
Yeah. More specifically, not X and not Y. You're also correct, because here you have X and Y, which are my two ones. That is also true. Right? So each of these OR terms is actually going to correspond to one of these rows. Lastly, we have X and not Y. So I need to find X, not Y. There we go. Now, I assert that this circuit and that circuit are the same. They're equivalent, the same. So this one is needlessly complicated. Now, it's not like you're just going to see that and know that. We're going to start doing some tricks. We're going to start learning some rules of how we can simplify that. Now, the hard way of doing this would be start doing some algebra, right? So I could factor out the X on that one, and then maybe do something with the factor out Y and try and start simplifying. But we wouldn't really know, we'd have to think about it. But that's where these nice little rules start coming in handy. Oh shoot, I should not have erased that circuit. Do you guys all write down that? We'll come back to it. I will leave that up though. Okay. So this is what we call Boolean algebra and the theorems that are associated with it. Now, we have the easy ones. We have what we would just call properties of 1 and 0. Which simply state, these are on, page 31 of your book. They're going to be very important, like really important. So Write that down, know where the page is. I'm going to go over some of the more important ones, but let's start with saying x or 0 is equal to x, right? Because the or 0 can never be true. So the output only depends on x. Similar happens with x or 1, right? We've talked about this one before, because if it's or 1, the 1 is always true. And based on the truth table of our OR gate that we had up earlier, that's always just 1. Now, you have some other ones. This one, indepitent or something weird like that. Rule x or x is x, right? I kind of talked about that before because I can't change one without the other, so they're just mirrored. Same goes for x and x. They're mirrored, they don't change. And because the AND gate is, if they're both 1, the output is true. So it would just be saying 1 and 1. It would be like connecting the AND gate like that, right? Okay. What happens to that? So here you start thinking about plugging in the values. What is the value? What is the output if x is 0? So x is 0 is false. What is x bar?
It's good, true.
True, yeah. Because if x is 0, x bar is 1. Therefore, 1. Similarly, if x is 1, then x is 1 and x bar is 0, but it's still an OR, so it's 1. So this is always 1. Similarly, if you have x and x bar, it is always 0. Because you can never have x be the same thing, right? And in order to have an AND gate be true, both inputs must be true. So that's always 0. There's some other ones that are just like from algebra, if you remember, like your associative and distributive. We kind of talked about the distributive. Commutative, which is just saying the order of operations doesn't matter, right? Like A and B is equal to B and A, right? Just like multiplication. Pretty intuitive here. Now we're going to get some that are more specific to logic. So, but we've kind of hopefully started building up a little bit of intuition of what these are going to be. So if I have x or x and y, what is it equal to? Does the y matter? No, because it's x or x and y. So this is a part of that. So in order for, if this is a 1, it's already true because of the OR. So it doesn't matter. So x or x and y is just x, right? We talked about that one before. This one is a less intuitive. And this one is fun. It'll show up on an exam in complicated ways, I promise you. So if we have xy or x not y, only x matters. And we know that y. what happens if I factor out the x or the y bar, right? We can just start doing some simple factoring and start seeing that the y doesn't matter, right? Because x and y or x and y bar, it doesn't matter, right? So I have both options here to choose from. Okay, here we go for the most complicated of them all. You will hear this, you'll be tested on this one, and it will drive you crazy because it drives me crazy. It's called De Morgan's theorem. And what De Morgan's theorem states is this. Another way of writing that don't worry, I'll walk through this because this one is complicated and I still screw it up. But it's really important. So the first thing I want to point out, because people always screw this up, it is very important. These are not the same. And we can do a truth table to show why. But when you have the bar over the whole thing, that's like saying the AND gate is knotted. So remember my inverter, it has this bubble. So the output is X and Y. Okay. X and Y inverted. The bar goes over the whole thing. X bar and Y bar is right. These are subtly different, but they're not the same. Don't confuse them. Like half the class misses this. This will be on at least one of your exams, possibly both midterms and the final. Like, it's an important idea. Okay, so now that I've made that hopefully painfully clear, let's go ahead and talk about De Morgan's theorem. Now, what De Morgan's theorem states is essentially you flip any OR gates to AND gates, and then invert all of the variables, right? So here, they've changed the OR gate to an AND gate, and we can make that explicitly clear if we want with the dots. You don't need the multiplication sign, just like in regular algebra, but if it helps you think through it, it's good to do, right? So flip this ORs to ANDs and ANDs to ORs, so OR to and then invert the X and Y. Same thing, other direction. And goes to OR, flip the X and Y. Don't worry, we'll do like, I have a better example that's going to build up, and we're going to start seeing some fun Boolean algebra, of which Boolean algebra, using these properties I just discussed to simplify things, is going to be like the first homework assignment. Okay, so let's go ahead and simplify this. Now, this is very difficult to go and draw just as a circuit straight away. Anytime you have a single bar over multiple terms, start suspecting that you're going to have to do something with De Morgan's, because it's really hard to manipulate any other way. So the first thing that I want to point out is you're going to separate this into terms. Not down to like the individual elements of it, but here we have an and, right? We're anding this and that. A or B and C or D. We're going to start there. We're not going to try and simplify it all the way in one go because it's impossible. So what we do using De Morgan's is we flip the sign and then put a bar over all of them, invert them, right? So the first step is saying this is equal to. Now, I don't put bars over the individual A and B because that's not what I'm using De Morgan's theorem on. I'm doing it on the whole thing. So the whole thing gets a bar. And then this and turns to an or. It already has a bar, but we're doing De Morgan's, so it gets a bar. This is saying not X, right? It's a double negative. If I add a third bar, it goes back to not right. They can start stacking. In other words, that. But we're not done, right? Because I got this that came out. Now I have to do De Morgan's again, but only on these guys. Take just a moment to flesh this out, and then I'll write up the answer. I want to make sure you guys kind of can do it. So next row of simplification. What is that equal to after performing De Morgan's on this?
So not A.
Yep.
And
not A.
And B. And not B.
Exactly. And not B. And not A just is A. I'll give you some homework problems on De Morgan's theorem. You'll build it up. We'll practice this abundantly. Okay. So I guess the question then becomes, we've had De Morgan's. De Morgan's isn't going to help us simplify this, is it? Right? Because there's no overarching bar. But hopefully we have some other tools that we can start using to simplify this. So I'll write it again over here just so we can get to it. Okay, so does anybody see somewhere where we can apply one of those theorems I just talked about to simplify this function? What do you see?
X_y plus x not 1.
Yes, exactly. And what is that equal to? Perfect. Does everyone see that? because you have x and y or x and not y, so the y doesn't matter in that one. Okay, can we simplify that one then?
Should we use De Morgan's to break into some or statements?
You could, but that would actually make it a little bit more complicated. You start thinking De Morgan's anytime that there's a bar over multiple terms. When each term has its own bar individually, that's not quite what.
That's right. It would just lead to one.
Yeah, yeah. So what we're looking for then is, I'm going to get the name right on this one. Sorry, I always forget it. But you can see where the issue is. Can anybody like just intuitively feel what the issue is, even if you don't know the theorem? What stands out to you? You have an x and a not x, right? So even if you don't know the theorem that says this, you can hopefully start to build up this idea that if you see those two kinds of things, that something is going on. And if you don't know the theorem, you can factor, right? What happens if I factor out? Well, I won't do that to you because that requires two theorems actually. But actually, maybe I can't simplify that one. No, I absolutely can. Okay. Sorry, I'm trying to find the right theorem because I know I can simplify this one, but I didn't write it in my notes. Oh, I think it's absorption, but it's not quite right. All right, maybe that's as far as I simplify. Sorry, I'm just going to pull out the book. I know it's in there. I know there's something I'm not seeing, and I forget this. What? Page 31. Oh, that's funny. I wrote it down wrong to start with, but that's okay. I'll figure it out and I'll post the answer once I figure it out. This is why we do homework, so I'm out of practice. Sorry, guys. There's something weird with that one. So this is actually a really good opportunity. Sometimes I like screwing up because what we can do, truth tables are your friends. Because sometimes things that aren't apparent in the equation become obvious when we write out a truth table. And sometimes they'll just help you realize that you did everything right and you're just being suspicious of yourself for no reason. So if we have x and y, f, we can say, when is this true? Well, if x is ever true, right, it's true. So in both cases where x is true, we get 1. Then the only thing left is when we have not x and not y, not x, not y. Well, now we feel pretty good, right? We have the more complicated one with its truth table and the simplified one with its truth table. We simplified it right this far. We didn't make any mistakes along the way. But then we start asking, well, like, what did we miss? Because the only time it isn't true is if x is 0 and y is 1 is the only time that it's not true. And so if you left it there, you're getting most of the points. You did the hard part. But here you can start kind of thinking your way through what it is. I won't waste any more of the time. I'm missing something obvious, and I won't puzzle through it. It's an important theorem, and I always forget this one because it's really weird, but I'll get there. Okay. As I said, I will give you homework with the theorems on it so that you get all the practice that you need. And if you get stuck, remember, I have office hours. Nobody ever uses them. I can help you puzzle through and we can be confused together. How do I want to do this? Okay, so some of the homework problems, and this is not like a real tool that you're ever going to use out in the industry, but it's kind of to help you start visualizing the logic. They're going to ask you to use the Venn diagrams to prove the two things are equal. So let's do an example of that. So let's say that we want to prove that, I'm going to drop this pen, there we go, X and Y, or X, R and Z, or Y and Z is equal to X and Y, or X bar Z. And I'll see if I can do this without the notes and screwing it up, right? So we're trying to assert that these two are equal. We could go through some of the Boolean algebra theorems and prove it. But the goal here is to kind of step back, breathe, and help visualize what's happening with these. So we're trying to build up your intuition so that you can kind of look at something and be like, something here should simplify, right? If we look at this, we start going, well, I've got, I don't know, Z, Z, Y, Y, like, I don't quite know how to, simplify that down just by looking at it. Well, we can start building it this way. So we've got X, Y, Z. And then I can start stepping through and shading in the portions that are here, that are true, right? So X and Y, that section. Not X and Z. So it's Z, but not X, right? So this section is actually colored in because it's Z and not X. We don't care what Y is on that term. And then it's all of this term, right? Everyone see that? And then we have Y and Z. Y and Z. Oh, well, it's that section. That whole term didn't matter, did it? Okay, well, let's just go check the other one. Oh, wait, I did miss one section. Y and Z is also true in the very middle. Almost missed a dot. Did matter. Okay, again, X, Y, Z, and we say X and Y. Well, we already did that term. Apparently that term's really important. And then we have not X and Z. Sorry, did I screw something up with this one? Oh no, yeah, because that one doesn't fill in there, Y and Z. Huh. Because this one doesn't fill in that one. Everyone agrees? X and Y, X and Y. Ow! Ha! Ha! We don't care about Z. That's why. Sorry, I get confused sometimes. I don't. Did everyone see what I did wrong? Is anyone confused? What I did wrong, just if the video viewers end up being confused, is I failed to recognize that the X and Y should extend all the way down into that middle section, because that is still X and Y. We just don't care about what Z happens there. So it is filled in. So if you don't get confused like I just did, hopefully your two Venn diagrams end up being the same. So the question might be, prove that they're equal or evaluate if they're equal, right? And so be careful with it. And the prove that it's equal is a lot easier because, right, you know what the answer is supposed to be. If you're trying to evaluate if, go step by step, go back and look at it and make sure. Because I will be the first to admit, digital logic is easy to screw up on because it uses a part of your brain that you're not really accustomed to using. You're going to have to kind of exercise these kind of muscles as you go through and like logically parse out the circuits. And some of you are going to be like better at it than I am before the end of the semester, just because some people are better at this than others. It's just whether it kind of works with your brain or not. But everybody can learn it. I've never seen anyone really too struggle with enough practice. You guys want to do another one of those examples, or you feel okay? Is there any other things that I've done here that you want more examples on? You're just really quiet or you're really confident? All right, I like it. As with the theorems, the only way to really do it, like understand it, is just to do it a bunch. So the assignments are kind of important. Okay, we're moving really fast, actually. So I guess good news for everyone. 5 to 8, right? Okay, so what we're next going to talk about is more vocabulary, unfortunately. But it's important vocabulary that will come back around in just in a little bit. The words are min terms and max terms. So the min terms is something you'll deal more with. And the definition of a min term is a logical expression that is true for one and only one row of the truth table. Okay, that doesn't make a lot of sense. Let's draw it out. So let's start with a new truth table. Let's make it a little bit bigger. We're going to have 3 inputs, and I'm going to say, let's make a truth table for prime numbers. We're going to make a prime number detecting circuit with a 3-bit number. How do we do this? Well, all truth tables start the same way. We're going to do something like, this is actually kind of a helpful hint here. As you start getting bigger circuits, start writing the ABC in reverse. ABC, right? And now you can count up in binary, or you can use the trick that I like because it speeds it up. 0, 1. Right, so I just alternate it, and then I do 2, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, right? Easy trick. And now what I've said is I want prime. So not a prime. 1, technically not a prime. And then, sorry, so to help familiarize it with, right? And I don't fault you at all if you do this for the first while, 0, 1, 2, 3, 4, 5, 6, 7, right? So if you want to write the decimal number down next to it, just help you remember what you are. Is 2 a prime number? Yes. Is 3 a prime number? Yes. Is 4 a prime number? No. 5, 6, and 7. Okay, boom. We made it. We did it, right? So now the min term is a statement that is true for one and only one row of the truth table. So let's go with the first prime at 2. What is 2? Well, it's not C, B, not A. Go ahead and fill out the min terms for the remaining ones. And I'll come back and do them and make sure you get them right. Okay. What's this? What's the min term for this row?
Not C, B, A.
Absolutely. Who wants to take a stab at 5? Min term for 5. Go for it.
So C, B, not A.
So you got 5 is C, not B, A. Almost. 7, who wants to take the easy one? What's the easy one?
CBA.
There you go. Yeah, that's our favorite min term. Now, the great thing about min terms now is this is super easy to make into an equation. Super easy, because you just OR the min terms together. Again, if you're doing long ones like this, I recommend just doing write them all out and then go back and fill in the necessary bars. There's our function. Nice and easy. Now, it gets better because this is really easy to turn into a circuit, isn't it? Does everyone see how you would do that? Right, because you just have 1, 2, 3, 4 AND gates all going into one 4-input OR gate. If my terrible drawing ever confuses any of you, yell at me. But right, so this one is just C bar, B, A bar. Right, that's this midterm into the OR gauge. And here is F. Now there's probably some simplification that we can do here. So I could go further and I could ask you, and I will ask you, probably on an exam, to write me the simplified sum of product terms for this truth table. What you would do then is write out the truth table, write the midterms, write the function, and then start simplifying that function. But if I say sum of products, that means that you don't ever need to simplify something to be factorized. So you wouldn't, for example, need to take this midterm and that midterm and say factor out the BA. You could though, because it turns out that simplifies the circuit, right? But if it didn't simplify the circuit, you wouldn't have to do it. So let's do it. Factorization is really great. So this guy and that guy, we can say BA or and, right? We factored C bar or C. Right, that's just factorizing. What is this? Well, what is this specifically? Just one. Because B and A and 1 is just B and A. Right, so I just used 2 of our little theorems to make that simplification to cross out this guy and that guy. Are there other simplifications that we can find? I don't know. I'll sign this as homework. You go figure it out. There's one more. But yeah, this one's not too bad, right? But that's what you'll do, is you're going to write out the midterms and start puzzling through them. Now, there's another way to write this expression. And this is important. So, well, there's 2 ways. The first one I'll do is I can also say that F is equal to the midterms, and the midterms are numerically ordered. So this is midterm 2, because we're 0 indexed. Does everyone know what that means? So 0 index means you start counting at 0. So this would be M0. This is M2. So F is 2, 3, 5, 'm, subindexes of where the 1s are, there. So I could literally ask you the question again, please simplify the expression for me of this. You may then have to go write out the truth table, write out where those midterms are to figure out what they are. With practice, it'll just kind of come to you. Well, some of you, it never stuck with me. I was never good at the shortcut. But there's nothing wrong with writing it out. Okay, so another way of writing this is I can go, please simplify this expression for me. Okay, all that's saying is please the sum of m's 2, 3, 5, and 7. Sum of the midterms 2, 3, 5, and 7. And then you just have to go through this, turn it into the equation, start simplifying. Okay, so the max terms. So that's min terms. Max terms are very similar, except for it's where are the zeros. That's all. You write the terms for the zeros and write out the expression. The difference is on the expression. Here we use capital M's instead of lowercase m's, and we use the capital sum of max terms 0, 1, 4, 6. You can also just do it this way, 0, 1, 4, 6. Right? I don't even need the m's if I want to do it this way, right? I could do that same way here. Right, so this is just some notation to describe this to create there. Rather than creating huge effort, it's just quick. Are we okay if I erase? I do want to say, you guys have noticed me making mistakes on the board. I'm not like embarrassed about it. If I'm working on something as you guys learn more and I screw up, or like you even think I screw up, call me out. I appreciate that when you can come if you're here, because seeing your guys' confusion on your faces when I do something weird is helpful to me to catch the mistakes. Like I don't have a massive ego on this. I'll make mistakes all the time. And I'm not going to judge you guys if you make mistakes. So don't be afraid of questions. Okay, I'm going to erase this now. Hopefully you've got time for that. Okay, now we're going to go back to easy mode. We all like easy, right? These are not all the gates in the world. There are more gates than this, and I'm going to introduce them to you now. So, much like with the inverter, how we just take a buffer and put a bubble on the end of it, we can do the same thing with an AND gate. This is now a NAND gate, a not AND gate. Whose truth table? Well, if we have a truth table of and, we can go ahead and say, well, and is this. And NAND is just not that. Perhaps unsurprisingly, we can do the same thing with an OR gate. What do you suspect they call that one? A NOR, a not OR. It's a NOR gate. Which again, you just take the OR gate, flip it, right? So we could go further, and there is another option for the OR gate. So let's write out the truth table for the OR gate, because this one is kind of fun and useful. Or NOR right? This is equivalent in both cases to that. Right, just taking an OR gate, sticking an inverter after it. They're the same thing, it's just much easier to draw. Okay, but there's actually one more type of OR gate. And we call it XOR, or exclusive OR. The difference being, it's only true if one or the other is true, but not both. Exclusive OR, XOR. Now, you can actually have an exclusive NOR gate called an XNOR gate. That one is very rare. The XOR gate looks like so. So I will probably, in your homework, throw you a question because this is kind of fun. So it turns out in digital circuits that a bubble just means not. Okay, right? So not or, not and. Well, it turns out this is kind of fun. This gate NOR gate is equal to that gate. Your homework, that really looks terrible, doesn't it? Equal to. They're the same. Your part of your homework, if I remember, will be to prove that using truth tables. Again, just to familiarize yourself with truth tables. Okay, so there's one last thing that I'll get to. If I erase this. Okay. So we've talked about the sum of products. Now, I have the ability to ask you these same types of questions with something called the product of sums. Be careful not to confuse these two. Now, sum of products is way more common. These are kind of like gotcha questions, like make sure you read that. And all the difference is say something like that. Right, this is the product. So the final output gate is the and instead of an or of sums. So instead of being and gates into an output or gate, it's or gates into an output and gate. Like so. Except for those with the OR gates would need 3 inputs. Sorry. I have budgeted time next week to come back and kind of revisit some of the Boolean algebra stuff because it's really important and it gets tricky. There is homework that I've posted that's due before, like, I don't know, Monday at midnight or something like that. It's not hard, it's just stuff that we've covered here. I'll go back and make sure I didn't forget something, but I'm pretty sure it's like the Venn diagrams, it's got some of the Boolean algebra. I don't even think it yet asked about the gates. I'll be adding some of that. You'll go and do it, and then and even though it's due, it'll be due at midnight after this class, so a week from today at midnight. Try and get it done before then, so that when you come and we're talking again about the Boolean algebra, you have kind of questions, right? That you know if you're struggling somewhere, so that we can kind of address these with examples. We have, let me think. There are examples in the book that I didn't go through for some of the Boolean algebra. On page 33, according to my notes. Yeah, so on page 33 and 34, there are two examples that I've left for you guys to walk through on your own, so that you can go and like try it, right? Go look at them as their problems, try and solve them, and then you have the answer there for you. Don't make the mistake of being like, oh, this is so easy. Because what happens to engineers a lot, engineering students, is in class you look at it and be like, man, that is so obvious. And then you go home and you're like, oh, goodness. And it's not like a judgment on you guys. Like you saw what happened with the truth tables, right? I mean, I'm pretty experienced at this stuff. And I looked at the equation when I was in my office and was like, I don't know, I'll just solve it on the board when I'm there. It's easy. And I screwed it up. So don't assume that you know it, because it's a trap. And that's true for all of your classes as you go through ECE. If you assume that you know something in class and don't practice it, you're in trouble. With that, just some kind of like closing remarks that I kind of forgot when I'm going through the syllabus. The exams in this class are going to be take home, essentially. The way they'll work is that you can take them from anywhere. That includes in class if you want to come. They're open book, open note, open internet. However, you are not allowed to create new internet content. So that means you can't go ask on a forum. You can't post to Chegg. You can't, Chegg, Course Hero, Stack Overflow, those various homework help sites. That is not allowed on exams. I don't care on the homework. Get whatever help you need on the homework, because the point of the homework isn't to get it right or wrong. The homework is to learn it for the exam. But on the exams, don't post to Chegg. I've already failed multiple students last semester because they were like, oh, it's online. I can, no. It's really, really easy to figure it out, because what you'll find out is that the people that post answers to Chegg are people that are trying to earn, like, I don't know, whatever the points that they get, so like they get discounted access. And that's true for Course Hero too. And they're just you guys. They're not any better at it than you guys will be. That's who's watching those questions, and they're wrong. And sometimes it's me. Sometimes I'll post answers. I see you guys posting them, and it'll be wrong, and then I fail you in the class. If you cheat on homework, you get a warning. If you cheat on the exam, you just fail the class. It's not worth it. My class isn't that hard. It's actually kind of fun once you get into it. We have all this, like, I don't know, it's kind of rough. It's like a lot of learning the vocabulary of a foreign language almost, right? But we'll start to build up steam pretty quick, and we'll start doing hands-on projects and labs pretty quickly and start seeing what we can do. My point is this: don't cheat, guys. It's painfully obvious. Because, like, I'll see your homework. I'll talk to you in classes. I'll see your questions. I know what you know. So if you do something weird on exam, it's super obvious. By and large, most people don't cheat, which I appreciate. Most people are just good people. Next off, I'm going to post a homework assignment. This will be the easiest points you get. It's going to have a figure like this, and you're just going to tell me where you sit. If you're an at-home person and you intend on coming, we'll have to figure out how to make that work, because everybody else here, this will be just your assigned seats. The reason for this is Weaver State is doing a really good job at contact tracing for COVID, and We don't want to send anybody home that wasn't in contact, but if you were like sitting next to someone, they will still quarantine you for like 7 days. So it's like 7 days, and then you take a test, and then you can come back or whatever. It's really, this class is built really well to take from home if you need to for a week. So anyways, what I'll post this is keep in mind where you are, and then you're just going to tell me what number you are. If you're online and don't intend on coming in, just post online. It's just going to be a text answer, super easy points. Real quick, if you want me to give your numbers, you're 5, you're 3, 11, 20, 13, and 16. I guess if you're home, you can kind of use those numbers to take a guess of where you could sit. So like 17 is a good seat, and I don't know, 22, 24, 29, 31. Those are good seat numbers. But yeah, super easy points. I'll post that soon. I think that's all for today. I think we're a little bit early, but I went through the syllabus faster than I intended. Not really a big deal, right? It's the first week, we'll end early. As we move through and we get to the lab, sometimes I'll end early and give you guys time to like ask questions on the labs, or ask questions on the homework, or you can take off early. Like a lot of times my classes don't make all the way to the end. You have a question?
So is the plan to do like lecture one day and the lab the other day?
Exactly, yes. So for this class, Monday's our lecture, Wednesday's our lab. The lab's just across the hall. Your card swipe should let you in. If not, you can talk to Susan up in the ECE office, and she should be able to help you get that card working, just to swipe in. You'll need the breadboard kit that says it's required for this class, and you're going to need the book. This guy from the library, you can find it online, probably cheaper than the library, or the bookstore offers it for. If you're running into financial difficulties, as I know is happening to lots of people, and you can't afford the book, talk to me, and I can work with you on a solution for it. It'll be harder, but there is a way to work around it. Because I know people have been disproportionately affected by this COVID crisis on the economy. Are there any questions, especially like where we're going with this class? Anyone doubting?
Do we have a lab on Wednesday?
We do not have a lab on Wednesday.
So just lecture?
No, you're free Wednesday. Enjoy it. Yeah. I don't like doing the lab the first week. It kind of helps you guys acclimate to the semester again, especially with the wild times going on right now, right? I think we can all breathe a little bit on Wednesday instead.
So I think the bookstore offers a digital one too. Is that one fine?
Yes, as long as it's 3rd edition. If you get the 2nd edition, that's okay too, but you're just gonna have to ask me what the questions are, or ask a classmate what the questions actually are, because the problems are gonna be different in the 2nd edition, but the content is very similar. So that is an option as well. Other questions? Great, excellent. Yeah, I'll post this assignment. Remember your number. The homework is posted. It's 10 questions, I think. It's not too long. I'm going to post some more, like I said, to have the gate stuff on there, because this book doesn't ask that questions, but they're really important. Yeah, good luck. I hope you guys enjoy it. This is a bit experimental, the layout for me, but I hope you guys enjoy it and learn a bunch, because it's was one of my favorite classes when I was an undergrad.